This project presents a novel multi-modality medical image registration method that employs data augmentation using CycleGAN. Medical imaging is the technique and process of imaging the interior of the body for clinical analysis and medical intervention. This project deals with brain scans, specifically CT and MRI scans. Each type of scan visualizes different features and is a different modality. Image registration is the process of converting multiple images into one coordinate system. Medical image registration specifically aims to determine the optimum transformation to align the anatomy of two medical images, one considered fixed and the other moving. We aim to align the moving image to the fixed one. Medical image registration has a variety of applications such as computer-assisted diagnosis and surgery, compensation for motion across different scans of a patient, and as a pre-processing step in image-guided surgery. Many registration approaches exist today such as affine registration, and iterative approaches such as symmetric normalization. Recently, deep learning approaches have emerged which perform well but require large datasets and hand-labeled ground truth values for predictive accuracy. Further, most well-performing methods today focus on monomodality registration and there is limited research done on multimodality methods. Furthermore, the existing methods have several limitations. Non-learning-based iterative methods are slow, and learning-based methods require expensive ground truth values and large datasets, motivating the need to consider unsupervised methods in data augmentation. Multimodality approaches are not explored much due to vast differences in image appearance and intensity. To bridge these gaps in the current research, we propose a 3D deformable multimodality medical image registration framework with data augmentation using CycleGAN. Our method is unsupervised and includes two steps. The first is performing data augmentation using CycleGAN to generate synthetic images. The second step is to perform registration using the synthetic images to learn the deformation field. We use the CycleGAN to perform domain translation between the CT and MRI domains such that we can generate synthetic CT or SCT images from MRI images and synthetic MRI images from the CT images. We use the voxel morph network to perform SCT to CT registration to learn a deformation field. Since the SCT is generated from the MRI, the learnt deformation field can be applied directly to register the MRI. With the CT we modify the architecture of voxel morph to suit our need of performing registration on two images, the SCT and the MRI. A notable innovation in our method is the joint optimization of mean-squared error between the warped SCT and CT, as well as the mutual information between the warped MRI and CT, including two metrics is observed to have greatly improved the registration quality. We test our approach on two datasets as shown. The preprocessing we use is resize and normalization. We also perform a fine alignment on the images from the CERMEPIDBMRXFDG database. Here we can see the images before and after a fine alignment. Although the teeth still remain visible in some scans, the neck region of the scan has been removed and the images also look more similar to each other. We perform threefold cross-validation and hyperparameter tuning to select the best model. The hyperparameters we tune are the weights of the mean-squared error and mutual information losses. We perform cross-validation only on the RIRE dataset due to time constraints since the CERMEPIDBMRXFDG database is larger and would take too much time to perform multiple rounds of training. Prior to performing k-fold cross-validation, we split the RIRE dataset into three parts such that for every fold, one of the three parts is used as the validation set and the rest are used for training. We then set the search spaces for the weights. The process first starts with selecting the first weight for mean-squared error. Then we select the first weight for mutual information. We then train the registration network for 100 epochs and test on the first validation set. Next, we train a new registration network for another 100 epochs and test on the second validation set. This is repeated for the third validation set as well, to complete the three folds of cross-validation. Then since we have exhausted all the validation sets, we select the second weight for mutual information and perform the three folds again. Once we have exhausted all the mutual information weights, we proceed to select the second mean-squared error weight and repeat the process again. We perform cross-validation in this fashion until all the mean-squared error weights have also been exhausted. In total we train 3 × 3 × 3, or 27 models in this manner. Once all the models have been trained, we select the weight combination that gave the maximum mutual information over all cross-validation rounds. The combination was found to be 0.5 and 2.0. We then train a new model with these weights on both datasets separately, and report the metrics for each dataset as the average over the held-out test sets. After k-fold cross-validation and hyperparameter tuning, We compare our method against 3 other methods, namely affine registration, symmetric normalization or SIN, and the original implementation of voxel morph. We report the highest mutual information and close to minimum mean squared error. We also report the fastest registration time. Here is a result image from each dataset. We can observe that the MRI has been warped to the shape and size of the CT, with some of its features altered due to registration. With that, we have reached the end of the presentation. Thank you for your time and attention.